Giant stars are featured in several books, video games, and science fiction films. What are the salient features of this type of star? These are much larger stars than our Sun, with rays ranging from a few tens to about 200 times the solar radius, located at the top of the Hertzsprung-Russell diagram. This diagram takes its name from the two astronomers Ejnar Hertzsprung and Henry Norris Russell, who developed it independently in 1910. It is a diagram that releases some stellar parameters, temperature and spectral class on the abscissa, absolute magnitude and brightness on the ordinate. Temperature is measured in Kelvin. The absolute magnitude is the brightness that the star would have if it were at a distance of 10 parsecs from the Earth. Finally, the brightness of a star is measured with respect to the solar one, set by convention equal to 1. In the HR diagram, there are different zones, where the different types of stars are positioned according to the physical characteristics mentioned above. The predominant evolutionary structure is the diagonal that starts from the upper left corner, where the most massive, hot, and bright stars are, to the lower right corner, where the less massive, colder, and less stars are position lights, called the main sequence. At the bottom left is the sequence of white dwarfs, as they are celestial bodies with effective high temperatures but not very bright. While above the main sequence, to the right, the red giants and supergiants are arranged, as they are very bright celestial bodies but at low temperatures. The giant stars mentioned at the beginning therefore fall into this last category. They are stars characterized by large dimensions and great luminosity. Specifically, the blue giants have a high surface temperature, even up to 50,000 Kelvin, and a relatively short life, on average from a few million to a few tens of million years. Because due to their large mass, they quickly burn hydrogen contained in their core. The red giants, on the other hand, represent an advanced evolutionary stage that is passed through by the majority of the stars once they exit the main sequence phase. That is when they run out of hydrogen in the nucleus. But would it be possible to colonize them, or colonize the planets orbiting them? Let's try to understand the feasibility of this project in this video. Could we colonize giant stars? The first big problem is the distance that separates us from any star other than the Sun. To reach Proxima Centauri, the closest star to the Sun, traveling at the speed of light, it will take us at least more than 4 years. So how do you get to the stars? Let's analyze the possible means, starting from those currently available, namely the chemical rocket and the ion rocket. Later we will analyze some theoretical possibilities which do not yet exist. Chemical rocket. The one used, for example, by the Space Shuttle or by Elon Musk's SpaceX. In chemical rockets, the propellant consists of the fuel and the oxidizer. Usually the two components are joined only in the combustion chamber of the engine, where reacting chemically they produce the high temperature gas, about 3,500 to 4,500 degrees Celsius, which is expelled from the rear nozzle of the rocket. The expulsion velocity v of the exhaust gases from the rocket, expressed in kilometers per second, is given by. From this relation, we note that v increases as t increases, and mu decreases. From here we understand because liquid hydrogen H2 and oxygen O2 are used, hydrogen is light and the molecules expelled are of low mass, mu small, while the reaction with oxygen leads to high values of T. The reaction that occurs in the combustion chamber is of the type 2H2 plus O2, 2H2O, which is the water production reaction. The physical law underlying rocket motion is the conservation of momentum. The rocket engine ejects hot gas at high speed from the rear nozzle, and this by reaction gives the rocket a speed in the opposite direction. The engine works best in empty space. The atmosphere hinders the expulsion of gases. The speed at time t of a rocket starting from a standstill is given by, in which v is the ejection velocity of the gases with respect to the rocket calculated with the previous relation. M is the initial mass of the rocket when stationary on the launch pad. mt is the mass of the rocket at time t while in flight. M divided by mt is the mass ratio. This relationship is known as the rocket equation and was derived from Konstantin Tsiolkovsky, one of the fathers of aeronautics, in 1896. It is still the basis of space propulsion today. It is important to note that Vt is directly proportional to the velocity of the exhaust gases. The higher V, the higher Vt. Unfortunately, the final velocity growth is only logarithmic as a function of mass ratio, therefore very slow. A typical chemical rocket with V equals 3.5 kilometers per second and m divided by m equals 10 can reach a final speed of 8 kilometers per second. Just the one needed to enter orbit at 400 kilometers altitude, the same altitude at which the International Space Station orbits. The travel times with a chemical rocket, however, would be prohibitive, at least in the span of a human life. To reach Proxima Centauri, the nearest star to the Sun, would take about 75,000 years, traveling at the speed of 17.46 kilometers per second, the same speed of Voyager 1 spacecraft launched in 1977, and now flying far beyond the Kuiper Belt. Despite this small inconvenience, would you like to travel among the stars on a chemical rocket? Let us know in the comments. Ion rocket. An ion thruster is a type of electric propulsion capable of creating a thrust of the vehicle starting from the acceleration of ionized atoms without the need to resort to high temperatures. The two previous relations also hold for it, in which typically we have V equals 30 kilometers per second, and with m divided by m, t equals 10, the final speed reaches 70 kilometers per second. Again, an ion rocket would not be a viable solution to travel in interstellar space because, given its very small thrust, it would still take about 20,000 years to reach the star closest to the Sun. In an attempt to find a viable alternative to chemical and ion rockets for interstellar travel between 1973 and 1978, the British Interplanetary Society developed the Daedalus Project, a two-stage unmanned interstellar probe with a nuclear fusion engine, able to travel at 12.2% of the speed of light and arrive in 50 years at Barnard's Star, a red dwarf located 6 light-years from the Sun, or in 300 years to Arcturus, an orange giant in the constellation of Bootes and its star Brighter. At the basis of the operation of the Daedalus, there is the interesting idea of a rocket based on nuclear fusion of deuterium and lithium to make the spaceship move. D plus Li 2He plus charged particles. Deuterium and lithium react with each other without loss of energy through neutrons, and the charged particles emitted can be contained and guided by magnetic fields up to the ejection nozzle. Unfortunately, it has not been yet possible to build this rocket, which would also be the basis of generational spaceships, hypothetical interstellar spaceships capable of traveling at speeds lower, even slightly, than that of light, self-sufficient and designed to host generations of human beings in view of a journey that could last centuries or even thousands of years. Again, there would be pros and cons. The pros certainly include low cruising speeds, given that you travel at a fraction of the speed of light, and therefore the time of travel can be measured in hundreds of years rather than tens of thousands of years. But there are also several questions still open. For example, how to maintain social peace for long periods. What if part of the crew mutiny for any reason? How to keep an artificial biosphere inside the spaceship for an equally long time. How to protect astronauts from ionizing radiation and cosmic rays. Have you come up with any other questions? Let us know in the comments. Another possibility is represented by antimatter rockets. In physics, antimatter is the set of antiparticles, having the same mass as the particles that make up ordinary matter, but with opposite charge. For example, an antihydrogen atom is composed of a negatively charged antiproton around which a positron, anti-electron, positively charged positron orbits. The existence of antimatter was theoretically predicted by P.A.M. Dirac in 1928 and experimentally demonstrated by C. Anderson in 1932 with the discovery of the positron. According to some theoretical studies, these rockets would allow to reach relativistic speeds, that is, consistent fractions of the speed of light, and the travel times to reach the stars would be noticed considerably. To reach a star like Canopus in the southern constellation of Carina, which has a radius equal to 71.5 times the radius of the Sun, 312 light-years away, it would take only 354 years, traveling at 0.88 times the speed of light. Would you like to travel in a spaceship propelled by rockets to antimatter? Write it in the comments. Even in this case, however, there are negative aspects. First of all, where to find a sufficiently large amount of antimatter, given that our universe is made up mostly exclusively of matter? One could think of making it through particle accelerators, but how to isolate it from ordinary matter and make it stable? How to keep it? In any case, even if a way were found to manufacture antimatter, it would be a long and expensive process. In case they succeeded in building these rockets, the first colonists of exoplanets should face another big problem: how to get the energy needed to survive. One possibility could be to build a Dyson sphere around a giant star to absorb all of its energy. Originally proposed in 1959 by British astronomer Freeman Dyson in the article in Science, Search for Artificial Stellar Sources of Infrared Radiation. The Dyson sphere is a sphere with a radius equal to that of a planetary orbit. It would consist of a shell of solar collectors or habitats placed around the star, so that a good part of the energy emitted by the star would hit a surface on which the energy itself would eventually be reused. But what and how many are the problems that humanity should face and overcome in order to create a structure of this type? First of all, find the materials. The entire mass of our planet would not even be enough to create an infinitesimal part of the structure. So it would be necessary to use other materials present in the solar system, such as minerals present on asteroids, for example. And these materials should be of considerable thickness and strength to adequately protect the Dyson sphere from impacts with any meteorites. If the construction of the Dyson sphere were completed, other troubling issues would immediately emerge. For example, what would happen in the sphere as the heat inside it increases? Would a ventilation system be enough to dissipate excess thermal energy? In the event of an intense stellar flare, how would the supporting structures of the sphere react? Another aspect that must be considered is the social one. It goes without saying that the project will have to be shared by all of humanity. But not only that, every single human being will have to be actively involved in the achievement of the supreme goal, probably for a period of about 10 millennia, if not much longer, overlooking what may be the social, cultural, ideological, religious, and political structures that will be necessary and functional to the needs of the project. This already allows us to glimpse dark and gloomy scenarios, not only in relation to what is today's concept of society, but considering the probable and inevitable degenerations. These could represent the stumbling block in which the whole project could be wrecked in a catastrophic way.